let f of x equal 2 times the integral from 0 to x of cosine squared dt. G of x equals 1/2 times the integral from 2x up to pi of cosine of t dt. Use the fundamental theorem of calculus to show that for all x, f prime of x plus g prime of x equals 1. And then there's a hint with some trig identities, which we'll get to. So first we need to understand the part of the fundamental theorem of calculus that we're going to use. So here's what it says. If you want to take the derivative of the integral of a very specific kind of integral from any number up to x, always has to look exactly like that, taking the derivative of this thing. And then I'm going to introduce a new letter here. H will be my new function, h of t dt. And the fundamental theorem tells us how to handle exactly this kind of creature, but it's got to be set up exactly in this way. And the fundamental theorem says that in some very real sense, the derivative and the integral are opposite. And so they kind of cancel. So basically you just get h of t. But then the thing is you don't plug the t in, plug whatever the x is in for this t. So our answer here would just be h of x. Okay, so we're going to use that fact a couple of times actually. So let's first start with f prime of x. So we're looking for the derivative of 2 times this integral. Okay, so great. So 2 times, I know constant multiples stay when we take derivatives. So now we're after the derivative of this thing right here. Oh, super. That's exactly the form that the fundamental theorem takes. So apparently, when we take the derivative of this thing, all we have to do is plug that x right in there and copy that guy down. So I think it's just cosine squared of x. So that's what we'll put right down here. And it's just that easy. We're done with f prime. Easy when you know how, right? Okay, now let's do g prime of x equals, so same idea. We're taking the derivative of this g function. Constant multiple of a half stays, so it's half times. And now we're taking the derivative of this piece right here. Okay, this is a little bit trickier to do. So what if we first rewrite it so that the variable is on the top instead of on the bottom, because the fundamental theorem is very picky. It needs a constant up to x in exactly that precise order. And these guys are in some sense in the wrong order. I want my variable term to be upstairs. So how do you swap the limits of integration? Well, you just do it. So let's see, we're down here now at pi. And then we're going up to 2x cosine of t dt. But we pay for it. It's not a high price to pay. It just says take the opposite of whatever it was. Okay, that's lovely because now the variable is up on the top limit, just like it's supposed to be according to the fundamental theorem. So let's just go ahead and use our fundamental theorem now. So we're taking the derivative of this thing right here. Okay, let's pay attention now. So we got that negative sign creeping in. And then times the derivative of this integral from pi to 2x of cosine t dt. And again, the fundamental theorem says, well, just take whatever this guy is right here and stick it there. Now, I'm not really bothered by the fact that it's 2x instead of x. I'm just going to stick that 2x where the t is, just like we did sticking this x inside of this parentheses. Sorry, I guess we really technically stuck it inside of there for the t. So that's what we're doing. So here we go, purple. So instead of cosine of t, it becomes cosine of x, but it's not x, it's really 2x in this problem. And we're done. Except it wasn't just x. And again, the fundamental theorem is really picky. And it says, okay, this is what you do when it's exactly x. But we know that if we have a derivative rule that tells us what to do when the variable is just plain old x, then the chain rule comes into play when the derivative is the same kind of pattern, but it's more complicated than just x. And so the chain rule says, all right, great. We just have to multiply down here by the derivative of the stuff. This right here is the stuff. And so we tack on the derivative of the stuff. The derivative of 2x is just 2. So right there we get our 2. And so then our simplified version, let's see, the 2 and the half cancel, and there's a negative in the front, so it's just negative cosine of 2x. And that is what g prime is. And so believe it or not, the calculus here is done. We still have some work to do because we're trying to prove that the sum of these two derivatives is always 1. That's an identity we're after. And the rest of this is just going to be trig stuff, which isn't technically calculus. So let's see if we can finish this problem here. Okay, so we're going to put these things together in blue. So f prime of x plus g prime of x is the thing we're asked to play with. So we begin with that. I'm going to copy the two calculations we just did, 2 cosine squared x, and then plus g prime. So plus over there, okay, it's negative cosine of 2x. All right, so far so good. Somehow everything is supposed to explode and become 1. Okay, 2 times cosine squared, I don't quite know what to do with that at this moment. So how about we just sit on that, but recognize that cosine of 2x is exactly one of these identities that was given to us. So we'll replace that cosine of 2x with the right-hand side of that identity. So equals, we're just holding on 2 cosine squared of x. And then plus minus is just to subtract. And then right here, we're going to put in the right-hand side of that first identity. So instead of cosine of 2x, it's exactly the same as 1 minus 2 sine squared, which we're going to put right in there. Super. Okay, so let's distribute that negative sign through the parentheses. So we get 2 cosine squared of x minus 1 plus 2 sine squared of x. Okay, and then I see 2 cosine squared plus 2 sine squared, and maybe some warning bells are going off, and if they aren't, then let me ring them for you and highlight that identity. We know that sine squared x plus cosine squared x is equal to 1 for any x. So what we have here is 2 cosine squared x plus 2 sine squared x, ignoring this little guy in the middle. So how about we factor the 2 out of the sine squared plus cosine squared. And then there's that minus 1 that was in the middle. So I factored the 2, grouping the two things together. And then again, according to the second identity, the stuff in the parentheses here, maybe we'll go with a highlighter instead. The stuff that's highlighted right here is exactly equal to 1. So let's call it 1. So it's really 2 times 1. Subtract the 1, lo and behold, equals 1. I didn't quite write that the same way, so let's fix it. 2 times 1 minus 1, and that equals 1. So we're done.